Welcome to Chapter 6.8, Partial Pressure and Dalton's Law. The partial pressure of a gas is the pressure that a gas in a mixture would exert if it were by itself in a separate container. So here the pressure of helium would be at 2, pressure of argon at 4, and if you add them together, then the total pressure is going to be 6 for ATM plus the 2 ATM that they would exert by themselves in a container when they are not mixed. This is basically Dalton's law of partial pressures. Indicates that the pressure depends on the total number of gas particles, not on the type of particles. Basically, you can just add up all of the pressures that are exerted by the gas in a mixture, and your total pressure is going to be the sum of all the partial pressures of those gases. In the previous example, there were just 2 gases, and so the P total, or the pressure total, is going to be 6, adding up to plus 4. If we had another gas that was involved, and maybe it had a pressure of 2 as well, then we would have a total pressure of 8. So all of the partial pressures add up to give you the total pressure of the gas in that specific container. So at STP, which we now know is 273 K and 1 ATM, that 1 mole of a pure gas is going to occupy a volume of 22.4 liters, and this is just showing us that even if we have just the nitrogen by itself and we have 1 mole, then it's going to exert 1 ATM of pressure. Okay, if we have 1 mole total of oxygen and helium, it doesn't matter what the gas is, those two added up together equals 1, and so it will exert a pressure of 1 as well. If we throw in a third, so our gas mixture is a third gas mixture, now we have oxygen, helium, and argon. Doesn't matter what the gases are, but the moles is what we're adding up, and it adds up to being 1 mole. And so we know that because of STP, at 1 mole, we'd have 1 ATM of pressure. So it's showing us that it doesn't matter what the gases are that are in the container. It just depends on how many moles or what pressure is exerted by each one. Okay, so the air we breathe. This is a great thing just for you to know, just everyday life, that you are breathing mainly nitrogen. 78% of the atmosphere is 78.2 is nitrogen, and then we have oxygen's next, 21%, and then you have some other gases, small amounts of gases that are including argon, water, CO2, and things of that nature. But when we say that the pressure, the total pressure in the room is 1 ATM, that means that we're adding up all of the gases in the room, so nitrogen, oxygen, carbon dioxide, all of those things, argon, all add up to be 1 ATM, all the partial pressures of those gases. So how would we use a partial pressure equation? Well, if we're given a situation where we've got a couple of gases here, we have a scuba tank that contains oxygen with a pressure of 0.450 ATM and helium at 855 millimeters mercury. First thing we have to do is we have to have common units. We either have to convert to ATM or we have to convert to millimeters mercury. So it looks like here we're going to convert from ATM to millimeters mercury because we know there's 700 millimeters mercury in 1 ATM to get 342 millimeters mercury, or the pressure of the oxygen. Okay, and so if we've got that, our pressure is 0.50 ATM, which we converted to 342 millimeters mercury, and we have a pressure of 855, so 342 plus 855 gives us a total pressure of 11,097 millimeters mercury. So all you do, add up all the partial pressures of the gases that are involved, and voila, there you go, you've got your P total. Okay, for a deep dive, a scuba diver uses a mixture of helium and oxygen with the pressure of ATM. Okay, the only thing that's different about this problem is that we are given the P total, telling us that the pressure of the mixture is 8 atm. Okay. It's telling us that the oxygen has a partial pressure of 1280. Okay. And it wants to know the partial pressure of helium. So basically, this is just algebra. So if we look at P total is going to equal the partial pressure of oxygen plus the partial pressure of helium. Okay, this time we know P total and we know the pressure of oxygen, the partial pressure, so we're going to be solving for the partial pressure of helium. Okay, so if we isolate the helium by itself, then it's going to be P total minus the partial pressure of oxygen. Okay. We also, once again, were given the units of atm and millimeters mercury. So we're going to have to convert our 8 atm, so 1 atm, 760 meters mercury. So our units can cancel, and that gives us this. That's our P total. Okay, I'm going to move on. Well, we'll keep going on here, and then the solution will be shown as well at the end. Okay, so now we've got to use this equation. We've rearranged it because we have P total. So if we plug in for our partial pressure of helium, so what we're trying to find, equal to P total, which is 6,080, and we subtract out our partial pressure of our oxygen. Okay, so we have an A, B, or C here, so that would be very similar to what you would have on your test. Okay, but if we do the math, we get 4,800 millimeters mercury. We get this. So there's really only two ways to ask this question. You either are given all the partial pressures and you just add them up, or the other way would be if you're given P total and you have to be given you have to be given 2 of the 3 variables here. So it depends on how many gases are involved. But you have to be given, all the variables but one. And here we have P total, and so we're trying to find just the partial pressure, so we can subtract the partial pressure of oxygen from the P total to give us just the partial pressure of helium. So let's check our answer here. So this just goes through what we did. We have 8 atm, we converted it to millimeters mercury. And then we subtracted from the P total, we subtracted our partial pressure of the oxygen, and that gave us this number here. So the answer was C, 4,800 millimeters mercury. Thank you, and this concludes the videos for Chapter 6.